The altitude of a star is its height above the visible horizon. When it comes to celestial navigation, the altitude is the angle that you measure with the sextant. For position fixing, it's all about comparing the actual altitude you measure to the calculated altitude that you would expect if you were in the position that you estimate. To do all of this, you need to be able to calculate the altitude of stars, and that's what we're looking at today. The actual process is rather complex. You need to compare your own position on the global sphere to the position of a celestial body on the celestial sphere. This all relies on a branch of maths called spherical trigonometry, and the complexities of that are far in excess of that required for navigation. If you are interested, check out the Wikipedia page on spherical trigonometry, which I'll link up in the description below. For our purposes though, we're just going to be using this formula. There are ways to find the altitude without using the formula, but they all require more books, as they've basically just tabulated altitudes for fixed values of latitude, declination, and local hour angle. I prefer the formula for a couple of reasons. Mainly, it's a better starting point for learning the concepts, but also, a scientific calculator is much lighter and cheaper than carrying all those extra books. So, what does this formula actually work with? The HC is the calculated altitude of the body, and this is the actual result that we're after. LHA is the local hour angle of the body, which we already used when we looked at finding azimuths in a previous video. Lat is the latitude of the observer, probably just your estimated position. And dec, that's the declination of the celestial body, and you get that straight out of the Nautical Almanac. Finally, the plus minus is determined by the signs of latitude and declination. If latitude and declination have the same sign, it's a plus, and obviously if they're different signs, it's a minus. So let's take a look at an example. Our estimated position is 35 degrees, 30.0 minutes north, 034 degrees, 03.5 minutes west, which places us somewhere in the middle of the North Atlantic. The time we're going to say is 8:15 UTC on the 15th of January 2018. I'm going to use UTC instead of local time, as that's just an additional conversion that we don't need for the purpose of this demonstration. The body that we're interested in is Vega, and we start by turning to the Nautical Almanac. I'm going to use the one from thenauticalalmanac.com, and you'll find the link in the description below. I want the daily page for the 15th of January. Firstly, the data for Vega. Its sidereal hour angle, or SHA, is 80 degrees, 37.3 minutes, and its declination is 38 degrees, 48.1 minutes north. To turn that into a local hour angle, we're going to need the data for Aries as well. So, at 8 o'clock, the Greenwich hour angle of Aries is 234 degrees, 43.4 minutes. Then we can turn to the increments and corrections pages, and we'll find the increment for 15 minutes, 0 seconds. We get that as 3 degrees, 45.6 minutes. Adding together the Greenwich hour angle of Aries at 8 o'clock, the increment for 15 minutes, and the sidereal hour angle of Vega, we can get a Greenwich hour angle of Vega as 319 degrees, 06.3 minutes. Finally, to turn that into the local hour angle of Vega, we need to subtract our longitude, and we're subtracting because our longitude is west. This gives us a local hour angle of Vega of 285 degrees, 2.7 minutes. If I've gone through all that too quickly, check out the video on finding an azimuth of a star, where I walk through a local hour angle calculation much slower and I explain it as we go along. So, coming back to our main formula, we now have all the information that we need. Local hour angle is 285 degrees, 2.7 minutes. Latitude is 35 degrees, 30.0 minutes north. Declination is 38 degrees, 48.1 minutes north. The sign of the latitude and declination is the same, so our plus minus option is going to be a plus. Finally, it's just a case of plugging the whole formula through the calculator. You have to be really careful here, as every calculator will handle brackets and things differently. Putting it into mine, I get a calculated altitude of 31 degrees, 54.6 minutes. So as long as you have a calculator, this method will allow you to find altitudes using only the Nautical Almanac. If you want to escape the calculator entirely, you can use reduction tables, fiddling your estimated position a little bit so that the LHA of the body and your latitude become round numbers, so then they'll match the tables perfectly. Unfortunately, I've been unable to find reduction tables with a suitable copyright so that I can make a video on it at the moment. If any of you do know of any, let me know in the comment sections below, and then I'll be able to make that video. Otherwise, until next time, thank you for watching, and goodbye.